Ever feel like huge scientific discoveries kind of just appear out of nowhere,
Mhm.
like magic or something? Like one minute nobody's heard of them, the next minute they're like, ah, explaining the entire universe. Well, today we're going to grab our metaphorical shovels and we're digging into a story. The story of DNA's double helix. We're going all the way back to 1953, the year it all began.
1953. Quite a year. It really was a pivotal year in the world of science, a time when the entire scientific community was just buzzing. They all knew someone was on the brink of a major breakthrough.
Yeah, and we love primary sources here on this show. So today we're going right to the source. We're diving headfirst into excerpts from the original articles,
Yeah.
published in Nature, no less,
Yeah.
by Watson and Crick and Franklin and Gosling. Now, these articles, they weren't just reporting a discovery. They sparked a scientific revolution.
Absolutely. It's not every day you get to retrace the steps of scientific giants, and we get to do it right from the source material. It's fascinating.
Exactly. It's like somebody just handed us a treasure map.
Yeah.
And we get to experience all the thrills of the hunt firsthand. Okay, so picture this. It's 1953. The year is 1953. And DNA is still this big mystery. I mean, we knew it was important, like really important, for heredity. Like DNA was the instruction manual, passed down through generations.
Yeah.
But nobody knew how those instructions were encoded. I mean, that was the million-dollar question back then.
Oh, yeah. Lots of people were trying to figure it out. Some of the best minds in the world, actually. There were all these different models for DNA structure being proposed and debated. Some were good, some not so much. Some were just kind of laughed out of the room. But the world of science, it was buzzing with anticipation.
Yeah, you could say it was a real scientific nail-biter. Nobody knew who was going to figure it out first.
Yeah.
All right, so let me quickly introduce you to the main characters in our story today. On one side, we've got Rosalind Franklin and Maurice Wilkins. They were using a technique called X-ray diffraction to try and get a glimpse at what DNA actually looked like.
Yeah.
And then on the other side, we have James Watson and Francis Crick. Now, they were busy building models, trying to fit all the puzzle pieces together.
And let's not forget the stage for all of this, the esteemed journal Nature. I mean, getting published in Nature, that's like hitting a grand slam, a scientific grand slam. All of a sudden, your work is on the global stage,
Yeah.
and everybody's reading it and debating it. I mean, all the brightest minds in science are suddenly interested in your work.
Yeah. Talk about high stakes. So let's jump into Watson and Crick's article, the one that really shook up the world. They came right out and said it. Boldly proposed a structure for DNA, two helical chains coiled around each other, forming that iconic shape,
Yeah.
the double helix. And to top it all off, they even included a diagram of it. It's deceptively simple when you see it,
Yeah.
but it's elegant.
That diagram, I mean, even with the caption saying it's purely diagrammatic, which I always thought was kind of funny, it really helped people understand. It played a key role in helping the scientific community visualize this groundbreaking new concept. Sometimes a single image, it can be worth 1,000 words.
No doubt. It's like the perfect visual shorthand for one of the biggest discoveries ever made. But why? Why was the double helix such a revelation?
Imagine this. You're trying to build something that can not only store an unbelievable amount of information, I mean, we're talking the blueprint of life here, but also something that can replicate itself flawlessly. That was the challenge the DNA posed. And the genius of the double helix was that it solved this problem beautifully.
Okay, so tell me, how does it do that?
It all comes down to the specific pairing of molecules inside the helix. Watson and Crick, they proposed that adenine, that's A, always pairs with thymine, T, and that guanine. G always pairs with cytosine. C, now this isn't just a random pairing. The shapes of these molecules, they fit together perfectly, like puzzle pieces.
So it's like a chemical dating service going on inside DNA. Yeah, kinda. But this pairing is essential for DNA replication. Picture the double helix like a zipper. When it's time for the DNA to replicate, the zipper unzips, breaking the bonds between those base pairs. Each strand then serves as a template, attracting free-floating A, T, G, and C molecules to form two identical DNA molecules. It's brilliantly simple and elegant, and it makes sure the genetic information is passed on almost perfectly every time. That's incredible. I love that zipper analogy. And speaking of elegant, I have to point out this line in the article Watson and Crick just casually mentioned, and I quote, "It has not escaped our notice that the specific pairing we have postulated immediately suggests a possible copying mechanism for the genetic material." I mean, they make it sound so simple. Oh, and by the way, we may have stumbled on the secret of life here, but it's no big deal.
Yeah. A classic case of scientific understatement, of course. They knew what they had done. They had provided a framework for understanding heredity at its most fundamental level.
A truly groundbreaking moment in science.
Oh.
But
Yeah.
every groundbreaking idea needs evidence. solid evidence
Yeah.
to back it up. And that's where Franklin and Gosling's research comes in.
Exactly. Watson and Crick's model was pure genius. But even geniuses need real-world validation.
And that's what we'll be diving into next, how Franklin and Gosling used X-ray diffraction to prove that the double helix wasn't just a nice idea, it was the real deal. All right, so let's take a look at Rosalind Franklin and Reese Gosling's work. You know their article was published right alongside Watson and Crick's article. Talk about a couple of scientific bombshells dropping on the same day.
Definitely a moment in scientific history. And they really highlight how important experiments are. I mean, you can have the most elegant theory in the world, but without evidence, it's just a nice idea.
Yeah.
Franklin and Gosling, especially Franklin with her expertise in X-ray diffraction, they really solidified things. They provided that final piece of the puzzle.
Okay, so X-ray diffraction. That sounds kind of intimidating, like something out of a sci-fi movie, to be honest. Can you break it down for us? Like, how do you use X-rays to figure out the secrets of DNA?
Okay, so imagine you've got this incredible, really intricate object, but it's hidden inside a box.
Okay.
You can't open the box, but you can shine a light through it.
Okay, I'm following.
Now, the way that light passes through the object, the way it scatters and creates shadows, that can tell you a lot about the shape of the object inside, even though you can't see it. That's essentially what X-ray diffraction does.
Yeah.
But with molecules...
Sounds like using shadows to see the invisible.
Basically. By aiming X-rays at DNA fibers and carefully analyzing the patterns they make, Franklin could start to understand the basic structure of the molecule.
Interesting. So what kind of patterns did her X-ray pictures show?
Well, the photos, especially one that became super famous, it's called Photo 51, showed a very distinctive X shape.
An X?
Yeah, a telltale sign of a helix. But more than that, Franklin's measurements, she was very meticulous, gave specific details about the size and symmetry of the helix, which really cemented things for Watson and Crick. Their model was good, but her work validated it.
That's really cool. I mean, it shows you how important collaboration is in science.
Mm-hmm.
Even when people are working separately, they could achieve incredible things together.
Absolutely. It's like each team had different pieces of a puzzle.
And when they put their pieces together,
Yeah.
they unlock this amazing discovery. Speaking of their articles, I gotta admit, there was this one part in Franklin and Gosling's paper that was a little over my head. All those technical details about their analysis.
Oh, yeah. Like they're just talk about the different forms of DNA and the specific things they were able to determine from the X-ray images.
I didn't quite get all of it, but it definitely showed how meticulous their work was. They weren't just speculating. They had the data to back it up.
For sure. That level of detail,
Yeah.
It's the foundation of any good science. It's a roadmap for others to follow.
Right. So to recap, we have Watson and Crick with this super elegant model of the double helix. And then we have Franklin and Gosling providing the experimental proof to support it. It really shows the power of combining different approaches in science.
Without a doubt, a real turning point in our understanding of biology.
And their discovery. It wasn't just about understanding a single molecule. It opened up a whole new world of possibilities.
That's a great way to put it. It's like they unlocked a door to a secret room in biology.
Yeah, and behind that door
Yeah.
lies the potential to change the world. So I think it's time we step through that door and explore the lasting legacy of the double helix. How has this discovery shaped the scientific landscape we see today? It's amazing to think how far we've come. I mean, back then, just figuring out the double helix was huge. And now, we're doing things with DNA that seemed impossible back then. It's like science fiction becoming reality.
It really shows you how important basic science is.
Absolutely.
Sometimes a single discovery,
Yeah.
it can unlock so many doors and lead to whole new fields of research.
This discovery, I mean, it's not just about understanding DNA anymore. We're talking about manipulating it,
Yeah.
changing it,
I mean,
using it to cure diseases.
we're talking about things like genetic engineering and gene therapy. We're literally rewriting the code of life.
It's mind-blowing. Can you
Yeah.
give us some specific examples, like what's happening in research right now?
We'll take personalized medicine. That's a big one. By looking at your DNA, doctors can create treatments specifically designed for you. They can even predict your risk for certain diseases before you even get sick.
Wow, that's incredible.
And then you've got agriculture. Scientists are using genetic engineering to create crops that are resistant to pests and diseases, even climate change.
So we could potentially solve world hunger.
Exactly. And then there's synthetic biology. which is a whole other level. Scientists are creating entirely new biological systems, things that have never existed before.
That sounds incredible.
It has the potential to revolutionize everything.
Yeah.
From medicine to energy production to cleaning up the environment.
It's both exciting and a little scary at the same time.
Yeah, definitely. We're entering uncharted territory here. And it's important to think about the ethical implications. We have this incredible power, and we need to use it responsibly.
I think this really highlights something, the importance of going back to the original sources. Like those Nature articles we talked about.
Without a doubt.
When we read those articles, we see how science actually works.
It's not always a straight line. From question to answer.
It's messy.
It's full of dead ends and wrong turns.
And sometimes it takes a team of brilliant minds
all working together
to finally crack the code. So for our listeners, if you really want to dive deeper into this, we'll be sure to link to those original articles in the show notes. Trust me, they're worth a read.
You might even learn a new word or two.
And who knows, maybe it'll inspire you
to
make your own discoveries.
The story of DNA, it's far from over.
And that wraps up our deep dive into the discovery that changed biology forever. Until next time, stay curious.